Hello. Hi, everyone. And good morning, everyone. We have people joining in for today's webinar. I think we can wait a couple of minutes to have a bit more people joining, and then we'll get started on our webinar today. Next generation battery systems, smart packing for maximum power. I'm very happy to see that we have people joining in. We really tried to have as many people and specific people to have an interesting discussion today. So let's just see if we have a couple of extra attendants and then we'll get rolling. I think we can wait maybe 1 minute extra and then we'll start. Today's webinar will be filmed, so I hope that's not an issue for you all. The recording will also be available later on our social media and on the YouTube channels of the different projects. A couple of more people joining in. I see many nationalities, many names. I'm just guessing for the nationalities, but mostly Europeans, I gather. You will see that our panel of experts is also very European from all around the place. I'm sure this will make the discussions even more interesting today. The webinar will be held in English, of course, to make it easier for everyone to understand. As will the slides as well. I think we can get started. So I will share my screen with the presentation. And we'll get started. Good morning, everyone, and welcome to this EU-INGENIoUS Battery Cluster event titled Next Generation Battery Systems, Smart Packing for Maximum Power. My name is Mathias Joussom, and I'll be your host for today's session. I am work package leader for the communication, dissemination, and exploitation of the NEXTBAT project. And I'm also working in the consultancy firm Zabala Innovation in the communication, dissemination, and exploitation department. Today we have plenty of experts who will be presenting all of our projects, but I'll get to that a bit later on. So we have a big list of experts, as I said. They will help us navigate the next generation battery systems. We're delighted to have you all here. So many people attending, that's very good. It means that there is a real interest regarding the innovative European projects. And they really are pushing the boundaries of energy and power density, lightweight design, and modular smart systems in next generation batteries. So you might see during the discussions that I am not the technical expert, but that's why we have so many experts in this meeting, in this webinar today, to go really in depth in the projects. So today, as I mentioned, we have several experts from 5 different projects within our cluster, NEXTBAT, BATS, VERSAPRINT, TEMPEST, and Extended. Each will present their latest progress and in their collaborative outcomes, demonstrating how Europe is shaping the future of sustainable battery technologies. If you have been following our series, this is not our first webinar. It's actually our third, and we're organizing a fourth one at the beginning of 2026. So please stay tuned on our social media, on our web pages, if you want to follow this and follow our progress in our different projects. We'll also be present at the Battery Innovation Days this year again. We were there last year. If you are curious about our projects, feel free to visit our stand in Graz, and we can have interesting discussions about the future of battery there. So before we begin, let me introduce our speakers. I'll try not to mess up all the names. We have a lot of great speakers today, and I'll start with Mohamed Morshed at Avesta, representing Extended. Hello.
Hello everyone, and thanks for your participation. This is Morshed from Avesta Battery Energy Engineering.
Then we'll have Dr. Manex Larranaga from CDTech, representing BATS.
Hi everyone, it's a pleasure to be here.
We also have Lionel de Palmos from CEA, representing VERSAPRINT.
Hello, I'm Lionel de Paoli. Sorry, just a mistake
I'm
on
very
my
sorry.
name. No worries. And I represent the VERSAPRINT project.
From VERSAPRINT, like you said. I think you didn't come alone, right? You were supposed to have also your...
Abdoulaye.
Exactly, Abdoulaye and Ndiaye.
Yes,
I haven't seen his camera on. And I think he might be joining right now.
He's here.
Well, he will be also presenting VERSAPRINT.
Yes, of course.
Great. We also have Katerina Fragiadaki, if I say it correctly. I'm not sure.
Yes, you did great. Thank you. Thank you for having me.
And you'll be presenting TEMPEST. And we'll also have Kamil Barcewicz. How did I do?
Hello, it's Kamil Barcewicz here, and I will be representing the NEXTBAT. You pretty well for the first time.
Well, great. Without any delay, I think we can get started then. Great. So let's get started on the section 1, improving battery pack energy and power density. We'll start with this first session focused on how we can improve battery pack energy and power density, a crucial step in enabling high performance, efficient, and lightweight battery systems. You can see the different presentations. We'll go through each project. And like I said, once we're done with that, we'll go to a Q&A and have a discussion between the different experts about the project, about the perspectives for batteries in the upcoming years, and the new technologies, and all those things. But let's get started with NEXTBAT first, and I give you the floor, Kamil.
Okay, thank you. So I'm Kamil and I work at IonCore as Senior Mechanics Specialist. And we are participating at the NEXTBAT project where we're making a semi-solid state battery module. And I want to talk about it from the perspective of IonCore. We are a tier 1 supplier. We have expertise in serial production since we made over 3 million batteries that maybe you are using every day. We have a strong understanding of the actual requirements of the automotive of all our clients. And that gives us this unique know-how how to make safe batteries that are also manufacturable in serial production and don't break the bank. And I will tell more about it in the next slide. So if you go to the next slide, yes. On the right, you can see the picture of the module that we have designed, one of the modules that we designed in the NEXTBAT project. It's a scalable module. Now it has 14 cells only, but it can be scaled to many more, even up to maybe 100. And now we have the energy density of 262 watt-hours per kilogram. But by adding more cells, like you would do if making a real use pack, you would also increase the energy density. But if you would make a battery pack, the scope of the project was to make a module. But if you would make the whole pack, maybe you can even skip the modules. You can go straight to cell to pack design and save on weight. And that leads us to the smart design ideology, that by reducing amount of parts, you can try to combine the function of parts into one part. And what we did, for example, in the case of the cell frame in our module, cell frames are these green parts in the middle. We were able to eliminate parts that were supporting the terminal bus bars. We integrated that function into the cell frame. And that's how we saved quite some weight. But of course, the pack will not be made out of air. We have to choose materials. And in this case, we went for standard materials like glass fiber, reinforced plastics, aluminium, but we also chose aerogels, which became pretty affordable in the recent years. And that leads me to one key takeaway from here, that you should always follow the market for the newest developments. If you follow the developments of the suppliers, you will notice that every year they come up with new materials that are actually better, that there are new manufacturing technologies that you can use to make a lighter and more affordable pack. If your knowledge is from 5 years ago, it can be pretty outdated, and you really need to know what are the newest technologies and materials to have this upper hand from your competition. But by chasing the highest parameters like energy density, you should not forget those things that can be hidden, like potential problems like condensation, like behavior of the battery during the crash or thermal propagation, like aging of the materials. And you should always test your batteries to come up with the influence of these things. And that can unfortunately lead to some penalty on the weight. You have to make bigger margins on your parts, and that can lead to like lower energy density. But that's something that we learned by making 3 million batteries, and that's something I would like you to remember making next generation batteries. Thank you.
Matthias, you are muted.
Thank you very much for the reminder. Sorry, I was just saying thank you very much. Kamil, will get back to you during the Q&A session, and now we can move on to the BATS project. Manex, I give you the floor.
Now,
and this time
I
you're
was
the one
the one with
exactly.
I'm muted. Okay, thank you very much, Matthias, and hi everyone. It's a pleasure to be here, as I said. And now I will talk about how we develop in BATS project a high energy density and power density battery system that can be modular, scalable, and for different applications. And for that, the main concept we followed was the cell-to-pack conceptualization. Mainly considering the application constraints, instead of defining low energy and power density level battery modules to develop the configuration of the battery system pack, we use the cell-to-pack conceptualization to integrate as much as possible battery cells in the main battery system unit that will scale up following modularity concepts. So as you can see here, we defined a reference macro cell configuration that we stack in a linear way to form the macro module, the unit that provides the energy and power requirements by the application at the battery pack level. With this scaling strategy, we make the best use of the available space for integrating the battery system, which allow us to dramatically increase and improve the energy and power density of the application. Next slide, please. Okay, after the development of the battery system, we show you here, we integrate all the electrical and electronic components in the design. We define the structural tray, and like this, we have the main battery pack unit that we integrate in the application. Next slide, please, Matthias. Okay, and like this, here we have the main application. As I mentioned before, the design we develop can fulfill the requirements of different applications. And that's mainly because, I don't know, from the very beginning, we integrate modularity and scalability concepts in the design. Since we have the flexibility to include as many macro cells as needed to meet the energy and power specification of the application up to the battery pack level, and thanks to the structural battery tray and system design, we can stack the battery packs on top of each other to meet all the application requirements. And with the same design concept, we can easily adapt to different use cases in the project. I don't know, and that's really important because that was one of the main goals of this project. And in this case, we developed a specific battery system for a high-performance marine application, off-road application, and to close the loop, we also address the second life application, making this a very interesting and comprehensive project. So as a summary, with this design, which integrates cell-to-pack conceptualization, modularity, and scalability concept, we were able to use the same core design to address very different applications, such as marine or off-road, while maintaining really high energy and power density performance. And in the next slides, you will see the last designs of each application. This is for maritime and use case. In the next one, we have the off-road. And as you can see, the main design concept is the same, but we use this scalability and modularity aspect to go use case by use case. And finally, in the last slide, we have to close the loop, the second life application, as we can use the main try of the off-road application to integrate directly in this second life application. And mainly, this is the main description of the design we are developing in BATS, that I think that it's really interesting. So I hope that you like it.
Thank you very much, Manex. I already see some questions coming in. We'll answer them just once we're
Okay.
done with all the presentations.
Yeah.
Thanks again. And moving on from BATS to VERSAPRINT, I give you the floor to present VERSAPRINT, Lionel.
Yes, thank you very much, Matthias. Let's talk about VERSAPRINT project. So VERSAPRINT, that's named is versatility and printability. So the main strategy of this project is to develop modularity, multifunctionality with the building block aspect. So I've developed 3 main building blocks to improve the performance of the battery. So first of all, at cell level, we developed a Kunil channel directly on the cell that it could be printable directly on the face of the cells, so it can improve the thermal aspects, thermal conductivity, and high the C rate, and it's a very good. We have a very good result at the end, and we can print directly with the silicone material directly on the cell, and we can have a channel around the 2 millimeters diameter, so it's with a good flow rates between each cells. And the second aspect of the building blocks at the module level, in order to develop and to have a multifunctional component at these steps, is to develop a multifunctional bus bar that we can have several functionalities at this stage. First of all, to connect the power, of course, and also to disconnect one cells in order to replace it at the module level. We can improve the versatility and the second life. And also we have added in this printed bus bar several functionalities like monitoring voltage and a sensor, temperature sensor also. And very good, at the end we have a very good result regarding the weldability, I would say, and also the thermal aspects. That it's a very good improvement in order to dissipate all the power, the thermal power. And on the system level, we have developed also a self-reinforced polymer called SRP casing with a special material, a lightweight material, in order to, at the end, the main target is to improve the power density and energy density with lightweight material, lightweight component. And we've done a lot of development in order to improve the printability at the large scale as the system and module level. And we have replaced the aluminum casing as the state of the art by 30% of mass reduction with the specific polymer, that's PETG. And we are also characterize these components in order to confirm the good result at the end. And yes, that's it on my side. Please, Abdoulaye. Next slide.
I think the
think
next
it's
slide.
later.
Yeah, the next slide is later. Correct. You're correct, Abdoulaye.
For the test, it is the second section.
Yes, it will come during the second section. Yeah, correct.
Okay, sorry. Okay.
No, there is no issue. But it's good. That way we had an introduction to you, Abdoulaye. And now we've all seen you, and we're ready and excited to hear you in the second half of the presentations. But we'll move out from VERSAPRINT project and move into TEMPEST. Katerina, I give you the floor.
Hello, I am Katerina Fragiadaki, mechanical engineer and a PhD candidate working in the Laboratory of Technology and Strength of Materials of the University of Patras, and I'm here representing the TEMPEST project. TEMPEST develops next generation safe by design lightweight batteries, including advanced module-free systems of lithium-ion and solid-state cells for 3 demonstrator types: compact, large-scale, and stationary. And in order to strengthen the Europe's global position, our objectives are to obtain higher recyclability levels, battery performance, and 15% lighter weight. So lightweight design is essential to reach high energy and power density, which is achieved by using composite materials for the battery housing instead of conventional metals. Our composite housings are made from the novel thermoplastic resin called helium, reinforced with chopped e-glass fibers and aluminum hydroxide particles that provide fire retardancy. Demonstrator 2 is made from a similar resin called Menzolite 0400, providing very similar mechanical performance. The material has a density of about 1.88 grams per cubic centimeters, whereas aluminum has a density of 2.7 and steel a density of 7.8 grams per cubic centimeters. This means that for all the project's demonstrators, a reduction of about 30% of weight compared to aluminum is obtained, and a 75% compared to steel is obtained. And according to the source energy savings by lightweighting, reducing the vehicle's mass by 100 kilograms lowers the energy consumption by 0.6 kilowatt hours per 100 kilometers. So by reducing structural mass, we directly improve energy efficiency and driving range, which is further emphasized by the GCPTR calculations, which is a measure of how efficiently the total pack weight contributes to energy storage, as you can see in the yellow frame. So I think it's very clear that lightweight composites are essential for achieving this high performance. Thank you.
Thank you very much. Moving on from TEMPEST to Extended, our last project for the first section. I give you the floor, Mohammed.
Hello everyone, this is Morshed from Avesta Battery Energy Engineering, and our headquarters is in Belgium. Mainly focus on the batteries, the whole value chain from cell to the recycling part. I just want go one step back regarding the project. First, the extended project is related to next generation of multifunctional, modular, and scalable batteries. For these two terminologies, when we speak about the modularity, we can have some examples. Modularity might look like the Legos that most of us have played with them, like small bricks, and we can make bigger things with them, or new generation of somehow phones that they try to have different gadgets, different cameras, and such a stuff. And then if we want to speak about the automotive sector, we can speak from 90-20, 90-30, that different types of engine and after World War came to have different chassis to the current states that, for instance, Volkswagen MEB platform, that we can have different types of systems for electric vehicles, long range, and with lightweight or heavier to the same system. So it's first understanding the concept of the modularity is like this. And in batteries, we have somehow a very similar story. And when we speak about the modularity, it means it should be modular, and we can use the same concept of the battery for our home applications, for electric vehicle, heavy duties, marine, and the aviation. But as all of you know, most of you know, we have the issues regarding the standardization in each of these concepts. When we have to use, for instance, the LFP battery based on the rules just for home applications, and for instance, in different types of different places of work, for instance, in China, you can use LFP battery for the buses. For EU, you can use NMC or different other types of chemistry, but with different types of standardization. So modularity is a very nice concept, but it has different types of challenges. And when we speak about a lower TRL, technology readiness level, it's much easier when we want really to push it on the market. The second point that we should consider for these types of projects, modularity and scalability. Scalability, we can speak about that. We have one module of 5 kilowatt hour energy, and then when we want to extend it to the higher level, its voltage came from 60 volt, which is low voltage and lower types of standard, and safer to the higher voltage, it will have some difficulties. So again, when regarding the scalability, we speak about home, utility, or other sectors. So if we can respect these two concepts, it's amazing. But when the TRL goes higher, it's really complicated. But there is two important points which are really common in all the sector of the market, is the price and energy density. If we have a product which is cheaper and it has a good energy density, for sure it will win the market. As most of you have spoken about the system, we have the same concept in this extended project. Regarding the mechanical design, as most of you have spoken, we will have a lightweight material usage, and then the way that we try to use the same concept and extend it for scalability and modularity, and some safety aspect that we can, for instance, using a smaller vent or bigger vent. But finally, the core of whole system will be the cell, and cell is responsible for mostly 70% of the weight of the whole system in all the system. And the thermal system is the same. But one of the most interesting points of the extended project that it has not been referred to the other projects, at least based on my understanding, is the extended project is not only able to have the scalability from the mechanical and thermal point of view, is able to have a control system on the cell level. When we speak about the cell level, most of the system works with one BMS, and the whole system controls by one BMS for 16 S1P to the current market trend 52 S1P and such stuff. But the level, if we go to the one cell part and we remove some of the cabling and go to the wireless, it's really a big step where we can have the control on one cell, and then we can extend it easily with removing the cable by the wireless system and reaching to the control of the system point by point. The other points that we can handle it better is the other techniques, not just using the Kalman filter or the Coulomb counting for the algorithms, the EIS real-time part, that in this way we can have the real-time data, especially for LFP batteries, that we have a very plateau curve, which is really complicated. For NMC batteries, as you know, it's very sharp, and it's not complicated to understand the concept of a state of charge with just some simple calculation. But when it goes to LFP, which has most of the market nowadays, with this push of low prices, the new techniques and cell level, if we can reach to the low price, we'll have the highest value on the market. So in a nutshell, two factors play the most important part of the game. Price with a high difference, and after that, the energy density. Thank you, everyone.
Thank you a lot. Now I see we already have a couple of questions in the comment section. That's great. We'll go to them right after. I just want to start with an open question, something quite vague. Everyone can answer. Just one at a time, I would suggest, just so that we hear everyone. So what are the challenges when increasing energy density? Does anyone feel like starting this? Great. Go ahead.
Can I?
Yeah.
Okay. So regarding the energy density and improvement, we have different issues in different sectors. For instance, for electric vehicles, is that the longer driving range, and the other parts, for instance, oh, sorry, another question. Without increasing the battery weight. This is the most complicated part from my understanding. And then for the portable electronics, we need the smaller and lighter. But when these types of things happens, the most important part is that we should consider when the cells more denser. For instance, even nowadays you hear about 600 kilowatt hour for cells, and we will have very big dense and big cells. And when we face the thermal management issues, and when this is the first part, then the issue that comes play is the safety. Consider for an NMC cell, we have 1.4 times 1.25 the thermal propagation runaway energy that a cell explodes. When the cell gets bigger, we have a bigger safety issue. These are the most challenges for the battery parts in the system level, and for the cell level, making thicker the electrodes, removing the electrolytes in the lab, it's very fine. But when we want to extend it, it's really a part. I mean, from the small part and in the lab point, it's very fine. But when it goes higher, it gets more complicated.
Okay, thank you very much. I have a question for all of you. What is the C rate of your pack? Maybe we can go in the presentation order. Kamil, can you start?
Yes, C rates of our pack. I would have to dig that out. We will be testing actually, that's something that will still be tested. We will test the fast charging, and we have a criterion to not reach over 55 degrees Celsius. So that's still to be established, basically.
Great. Manex, what about yours?
Yeah, in the BATS project, we have the opportunity to test in a down-scale version, that it's at module level, and we reach until 3C charging and discharging processes. And I have to say that it was quite impressive how the thermal management strategy developed by MIBA handled these high-performance charging and discharging profiles. So that's at least the peak currents we manage right now.
Next to VERSAPRINT?
Yes, on the VERSAPRINT project, it's directly linked to the final application, but for the cooling building block, the C rate is about 2C, about 100 amps, and for the bus bar, it's around 3C, so up to 150 and up to 200. So it really depends on what could be the final application and the overall modularity of the battery at the end, which could be the configuration between all building blocks.
Thank you. Katerina for TEMPEST?
Yes, for the solid state cells, the SSB cells, the C rate is 0.5. And for the lithium ion cells, the C rate ranges from 0.5 to 1.
And finally, extended project.
It can reach 2C for short time. It's for the peak.
Okay. Thank you all for your answers. So now I'll go back to the first questions and go through them in order. Mostly of them are directly specified for someone. I'll just read them out loud. So question to Kamil, how is the cooling arranged? What is the cooling media?
So we'll have aluminum plates between the pouch cells, which will extend outside of the module, and these will be contacting a cooling plate where cooling channels will flow through, and the cooling media will be glycol water, classical glycol and water mixture.
Then I have two questions for Manex. What is the total battery capacity of the marine project? And the second question is, what are the main challenges to have the battery compliant with the marine regulations?
Okay, the first one I don't have the main specific values. You know that the main application was for 160 kilowatts hour, and we reach up to 170 kilowatt hours. That's for the first question. And for the second one, that's a tricky one because the marine off-road, mainly the marine application, it's not so open. We don't know too much about this type of application as we know about the electric cars and all this stuff. So the main regulation, we develop a list of specific standards that we have to fulfill to develop the design of the marine application. And that was a challenge. But I have to say that in this project, the collaboration between the partners is really, really good. So it was really easy to work with FMF and different partners to reach all this specification and define at least the structure that we have to follow to develop this type of design to these applications. So the main challenge was to specify the standards and after that apply them to the design.
Very clear. Then I have two questions for Kamil. Can you explain venting concept briefly? And the second question is, did you do a TP test already? If yes, what was the result? How did you trigger the cell?
So the venting concept on the, maybe if you would go to the slide where we can see our pack.
Let me just go back real quickly. So this one.
Yes. So you see in the corners, you can see the opening in the cell frames. And let's start with the fact that this is just a module. A module on its own, it doesn't have a TP concept. It is always a combination of the module and the housing. So that's a very important part that is missing from here. Also, like cooling plate plays a big role in the TP situation. So just watching the module on its own and discussing the TP, it's a little bit, yeah, it shouldn't be done. But we have a concept. We have the holes here in the corners, and we are in our testing jig. We'll have also like space for the gases to escape through. So the point is to like get the gases out from between the cells to the outside of the module and then direct them to the outside of the pack. And then the nailing test. Yeah, we're going to drive a nail through the, like from the above here, as you can see from the picture. We'll make a little hole in the aluminum plate here, and we'll drive the nail into the thin side of the cell. We haven't done the tests yet, so cannot tell about the results. I
Yes,
hope this
they will have to follow
question.
the social media and the channels and the deliverables published publicly to know the answer.
Yeah, I guess so. That's quite a new cell also to us. It's semi-solid state, so quite a different beast from the NMC. So I'm curious myself about the results.
Well, great. I'll go back to the Q&A, and I think now we move to two questions to Katerina. First one being, have you done any testing for those trays in operating conditions with cell? And the second question is, who will manufacture the housings?
Yes, well, we haven't tested both the cells and the housings together yet, only single components in operating conditions. And the housings are manufactured by Fraunhofer ICT. The two demonstrators, D1 and D2, have already been manufactured, and the third one, the stationary one, will be finished at the end of the year.
Great. I don't see any other questions in the chat, but I have a couple for you all. So multiple times during the discussion, I think the trends came about. So how do you keep an eye out for the newest materials and developments in the battery sector? Do you have any good advice? Does anyone want to answer?
Yeah, maybe. So what I do is I follow up with actually the manufacturers. I go to events like Battery Show, FIMA, things like this, and get in touch with the suppliers. They are the first source of the information. They know the products that will still be coming, and they can provide you samples that you can test yourself. Then, of course, follow online webinars, just like something like this, but about materials. That's what I do in the technology development of Ion Core.
Is it pretty similar for all of our panel presenters today, or do you have a bit of a different one? I see some people shaking heads.
Okay, if I may, totally agree with you, Kamil, and that's really important. Develop the benchmarking process and all this stuff, and contact directly the main actuators of the development of these components. In our case, if we evaluate the technology focusing on the battery systems, we have the opportunity in CDTech that we cover from more or less, how to say, from powder to power, which means that we develop our own battery cells. So we have specific groups that are investigating deeply this aspect of new technologies of the battery system and all this stuff. So in this aspect, for us, it's really easy because in-house we knock the door and we ask about all these specifications. But about all the technologies and new aspects that we have to integrate in the battery system, totally agree with Kamil. So we have to work on this type of evaluations.
Great. Morshed,
Yes, it's very good points that our colleagues mentioned. Just one more point might be useful. Reading the papers sometimes work. For instance, when because most of the manufacturers comes from some R&D, and when we depend on just the manufacturer, mostly now is China, we are one step behind them. But especially now, there is a good opportunity for all of the organization in Europe, aviation sector for batteries that's not yet touched completely, and the defense sector. So most of the technologies come from R&D, and if we want to wait 1-2 more years, for the supplier, we lose the niche market, and we might lose our differences from the other companies too, especially in Europe.
very interesting. I wanted to ask also, for all the projects, how did you manage to make the design so scalable? Because I think scalability is something very important here. Does anyone want to answer first? Go ahead, Manex.
Okay, I mean, this was one of the main topics and one of the main objectives of the project, because we had to fulfill the requirements of different use cases. So the main idea is to integrate from the beginning of the design these conceptualizations of the scalability, modularity, and all these aspects. In our case, in BATS project, we developed the main macro cell, after that the macro module. So with this, we have the option to develop different size of battery systems to scale up for the use case that we have to fulfill. So I think that one of the main aspects to reach this scalability and modularity aspect is to integrate from the beginning in the design this conceptual aspect.
Does anyone want to answer this question as well? Okay, well then, if you have a question between your project to another project, you can go ahead either now, or we can talk about it in the second Q&A section. I'll just verify. I think we're good. Well then, let's move on to the second section, how we test and validate the project technologies. So this ensures our innovations meet the highest standards of safety, regulation, and performance. Since all of our projects are reaching the second half of its project, we can finally talk about this. The testing, the validation, this is very important, I think, and I'm very excited to hear your thoughts on this. We'll go through the same order as last time. NEXTBAT, you can start.
Yes, thank you. So, in ideal case, mechanical design or design in general should go hand in hand with the simulations from the very beginning, and that's what we try to do here in the NEXTBAT project. Like, since we have pouch cells, we went first with the simulation of the swelling of the cells. Cells during their cycling, they swell. You know, the lithium goes into the graphite and makes the cell swell. So, and it of course makes the whole module get under mechanical stress. We did finite element method simulations about that to see how the pack behaves then. And we followed up, or at the same time, we did also CFD simulations where we tested the thermal behavior of the whole module. The cells heat up during cycling, the bus bars heat up. This causes also mechanical stresses. That's what we did. Then we reiterated the design phase and simulated again. And now we are at the stage of building of the actual physical prototype. Once this is done, in a few weeks, we'll start the physical testing. And I picked several of the tests that we'll do here. I'm not the testing guy myself, but we'll perform the tests according to the ISO 12405. We'll start with the capacity measurement, where we will cycle the module several times from the lowest to the highest voltage limits of the cells at the rate of 1C. And after a few times, we'll see what the capacity is. We'll follow up with the fast charging. We'll charge the battery from 8 to 80% of state of charge, and we'll either run against the limit of the BMS, current limits of the BMS, and we'll try to do it under the 20 minutes time, so 8 to 80%. And then we'll keep cycling the battery, but then at the rate of 1C. We'll do it 4,000 times, and we'll see what the remaining capacity is. We'll also perform BMS validation, where we'll test the data acquisition and processing done by the BMS. And once we have a nice characteristics of the battery, we'll go to the safety testing. These tests are harsher. They can destroy the battery, so of course they are done after the performance testing. We'll go with the vibration tests, mechanical shock, and then to crown the whole project, we'll destroy the battery by driving a nail through one of the cells. And we'll see how the thermal propagation management solutions that we came up with work. We are hoping for no propagation, of course, That's what we have achieved at IonCore with NMC batteries, NMC cells. But this is some solid state cell, so we're curious about the results ourselves. Thank you.
Thank you very much. Moving on to BAT's project.
Yeah, Manex back again. So to validate our approaches, I mean, as all of us, we use the experimental and the numerical environments. In this presentation, I will present the main work we have developed in the project, but after that, we will develop different aspects that maybe I will mention at the end of the presentation. So as you can see, we developed the main experimental evaluation and the numerical one. And because I think that since both of them are something iterative and self-reinforcing processes. So that's, I think that it's really, really important. For example, in the experimental validation, while we are developing the main conceptual design of the battery system at CAD level, we first develop the preliminary cell level characterization to evaluate the performance of the battery cell and use the information as a reference to build and validate the cell level numerical models. This is at cell level. And on the other hand, to validate the preliminary design of the battery system and evaluate the performance of the approach we were proposing in the project, we develop a downscaled battery module, a battery module with the same components and same characteristics as the ones we were designing for the main application, but in a lower energy and power level. In this way, we evaluate the performance of our designs, high performance working conditions, and specific use case working profiles, in this case for marine and off-road application. And like this, we evaluate the response of the system. And I have to say that, as mentioned before, it was quite impressive. And of course, all this experimental information is really useful to validate the proposed design performance, but it is really useful too to validate the numerical models that we are developing. In this case, in the numerical environment, next slide, please. I mean, next one, and I think that, yeah, I missed one, I think. Okay, that was the one regarding the experimental one at cell level and at the downscale module level. And if you go to the next one, okay, and in the numerical level, as you can see, we have different approaches. We have the 1D electrothermal models that are more focused on system level performance evaluation, parametric strategies, all this stuff. Apart from that, we have specific models to evaluate the thermal runaway and venting processes at 1D and 3D. And these are more regarding the safety aspects of the battery system, which type of safety materials we have to integrate, how we proceed in this type of phenomena and events. And finally, we have developed, considering the electrothermal and environment, the 3D CFD numerical analysis. And this is really interesting to evaluate the 3D thermal response of the battery system, the hydraulic distribution, all these specific aspects, and to propose additional design solutions. And this is really interesting because those are more or less correlated with the experimental approaches we got. So it's really useful because we use the experimental information apart from validating our design to validate our models. And after the validation, we start with the optimization strategies and all this stuff. And finally, in the next slide, we have the mechanical simulation approach we got, because it's okay. So the thermoelectrical evaluation is perfect, and to evaluate how the battery system will answer in a specific working conditions. But apart from that, if you are designing a specific battery system, you have to evaluate the mechanical response of this system. And in this aspect, in this project, we split this evaluation in two working lines. The first one was based on the system level, where we evaluate all the battery system considering for the off-road and marine application, and considering a specific working condition and a specific standard for these use cases. And apart from that, we develop a more specific mechanical simulation only evaluating the battery pack, considering one train, integrating all the components, considering safety layers, structural layers, battery cells, cooling strategy, to have a more realistic and more specific mechanical response of the battery system. More or less, this is how we validate. So this is the approach we developed for until now, and now we will integrate additional evaluation and validation processes with a bigger level battery systems experimentally, where we evaluate all the mechanical aspects, all the thermoelectrical aspects, and all this stuff. But more or less, this is what I have to say in this aspect. So thank you very much.
Thank you. I think we can now move on to VersaPrint. Abdoulaye? I think you're currently muted.
Sorry. Abdoulaye for Open Mobility. I am validation group leader in charge of validation of component and product as cell, module, or pack. For VersaPrint, we will perform the test. So we have two approaches. The first one is the verification of prototypes for aeronautics and automotive. And the last one, it is a simulation for marine application. One of the main challenge of this project, it is the reduce of the total weight to optimize the power density. And the strength of VersaPrint is the building of prototypes. So for the moment, we have no requirement. We can go on the next page. So as I said, we have no requirement, but we need to check the state of the art of the capability for many applications. So we perform mechanical test, environmental test, and abuse test. But today we will do a focus for performance test according to the ISO 12405, like Kamil. And for this project, I am in charge of test for automotive applications. So to perform this test, we make some instrumentations to monitor voltage, currents, and temperatures. So we have one list of tests. The first one is energy and capacity at room temperatures. So the aim of this test is to check the impact of the AC of the assembly versus cells datasheet, or we can perform tests at cell level. So we hope we will have no impact of the assembly, for example, on the bus bar and so on. And the aim is to reduce the maximum the impact of that. Also, we have the same test, but at different temperature and different current. So it is the same as the previous one, but we will perform with 3 C-weights and 4 temperatures. So to be sure that we can go on the limit of the cells. And during this test, we can measure and calculate the voltage, the current, the energy, the capacity, the power at different conditions. Also, we have the test internal resistance. So this test is used to double check the quality of the assembly. We can make a focus on the contact resistance because for our project, the resistance are very important because it is used to for the determination of the max power. And if we have some issue on the assembly because we perform with 3D printed, so we can have some local overheating and overcurrent. So that's why we perform this test. Also, we test the load of the SOC loose to check the auto discharge of the system. because we have a direct relation between the SOC loss and the SOH, the state of health. Because we during the test we will check after 1 day, after 1 week, and after 1 month the discharge of the component without plug anything. Also, we have a WLTP test. So this test is to check if the AC is able to perform some driving according to the future application. So for the moment, we have no requirement. As I said previously, for the moment, we need to check and have a state of the art. So we have no requirement because we have on prototypes development. Thank you.
Thank you very much. Moving on from VERSAPRINT to TEMPEST, Katerina?
Yes, can I please share my screen because I have added, I've changed a bit the slides, or no?
You're muted, Matthias.
Good to know. Again, so yeah, I was saying I stopped sharing my screen. You should be able to do it. Yeah, we're seeing your screen.
All right. Thank you. So regarding testing and validation, in TEMPEST we perform a multi-scale testing campaign to capture both the electrical and the mechanical behavior in order to ensure safety, reliability, and performance of the battery systems, while providing experimental results for accurate simulations. So at the cell level, we evaluate the electrochemical, thermal, and aging behavior of the cells, measuring the discharge capacity and state of health at different operating conditions. At the material level, we perform standardized mechanical tests to extract reliable data for our models. And at the component level, we evaluate structural integrity of the housing at different energy levels and configurations. This experimental work feeds into the model validation process, allowing us to confirm that our simulations accurately reproduce real-world behavior. Component level validation occurs when the simulation and experimental process results align, providing a predictive framework for further testing and safety evaluation. Here we have a comparison, a transition between the physical drop tower testing to a validated simulation. And as we can see, both the force time responses as well as the inflicted damage is accurately represented for different levels of energy. We can see 7.5 joule and 30 joule. We can also see barely visible damage and visible damage for different geometries, composite plates, and the housing, confirming the reliability of the validated model. This allows us to use the validated model for different loading scenarios that can be catastrophic to the battery system, namely different cases of crash and ground impact. In the ground impact model, the cell pack is also being modeled using a homogenized approach for the pouch cells. So here we can see that with increasing actually severity of the impact, the cells might be affected, even though the housing maintains its structure. Whereas in the crash simulations, the housing, although it gets severely deformed, succeeds to protect the cells which sustain their mechanical integrity. And here, for our work on validation and structural integrity, we have also published the paper for you to check out. So thank you very much for your attention, and I'm open to any of your questions.
Thank you very much for the extra slides. I think it really helped everyone to
Thank you.
understand your project. I'll just share again my screen. I think you should see it now, and we'll move from Tempest to the next project. Extended. I give you the floor.
Hello again. As most of our colleagues have covered the whole concept, and this is the same. I mean the simulation 0D, 1D, and 3D, and then go to very nice rainbow pictures. They are animation. I'm not sure it's possible to run them here or not.
I don't think so, no.
Okay, so mostly as we have spoken, we do the 0D to consider the worst case, and 1D simulation and 3D, and then the part that I just want to add these new parts, because otherwise it's just repetition of the other part regarding the validating the approaches. Some parts that I think must be valuable to mention is that after these types of very valuable parts, I mean the simulations, the next point will be the test environmental level and for each part, and then the component test, and then the whole system testing which should be added. And the next important point that we can scale it up will be the reaching an MVP, minimal viable product, mostly in TRL5 or TRL6 is a very valuable part, but I think it has an exponential behavior if we want to reach the real market. When we do the test in a coin cell or in a part with a very limited conditions, most of the time it works and it is very valuable. However, reaching to the market might need much more effort, and these types of knowledge can be transferred if we are able to reduce the time to market. And one of the most important points that I most of the time I see is that in all the projects we have work packages. I mean, we test the 1D, then 3D, and then go prototype, and it works, or it has some errors. If we change the philosophy from the waterfall aspect, I mean A, B, C, to a more agile system, and when we finish A, go to B, then come back to A, and then go to C. In this way, we can reduce time to market. And most of you know, if we have the right approach in this period of time, we can have the right mass production. Just consider that 75% of the errors in mass production happens in the design phase. It means if we have it's like a snowball. If it is a small error in the design, then in mass production, it will be a failure. So it means if have the right design process, this nice mechanical crash test, thermal simulation that makes hours from really engineers, they are not just some rainbow pictures and simulation. They are the whole idea, and later these types can be used to reduce the amount of the whole test system. Just one more point, that in some of our projects, Abby, I think this is a big concern now, even nowadays, regarding the thermal runaway. Thermal runaway, it's not just related to the cell, it's mostly related to the system. For instance, in our test we have done for zero thermal runaway for different applications with NMC cells, high energy density, more than 150, more than 169 ampere hour for NMC cells. So if anybody is interested, we are very interested to collaborate, that we have proven, we have taken the certificate, and we have done different types of tests to write based on the right simulation and reaching the result in different applications for marine and home applications. Thanks again for your participation.
Thank you very much. I think you really wrapped this up perfectly. And now we can move on to the Q&A. So far, we only have 2 questions in. We'll wait a bit more of the questions, but I can start with one. What are common challenges in battery system validation? I think that's quite generic. It can serve all projects. So I'd love to have all of your points of view on this. Does anyone want to start? Well, then let's go by the order we did during the presentation.
So I guess it's me again. So the question was common challenges in the battery
system validation. Yeah.
Validation. Yeah, I'm not from the validation team, so maybe it can be a little bit difficult to me. But I would say one of the challenges is actually high cost of the whole testing process and the time it takes. That's from my point of view.
Sounds reasonable. I think we can move on to Bats.
Yeah, I think that the validation process, I mean, for that, first of all, you have to define the references that you have to use to validate the approaches. And this is for all the projects. So it's really important to define properly the main references that you are going to use as a validation. For example, if you are working as in our case for a marine application, you have to evaluate specifically that to validate the design for a specific use case, which type of standards or specific use cases you have to fulfill. So in each case, you have to different generic standards to fulfill in battery system applications, but apart from that, you have to specify the other ones. So I think that this is something common for all the projects.
Next in line is VERSAPRINT.
For my side, the challenge is to perform tests with prototypes because they are not validate because we perform maybe 4 or 6 parts, and with these parts they are not very safe. So perform tests with no safe parts could be a challenge for us.
Interesting. Tempest.
Well, I'm not an expert in batteries. I'm in composite materials, so I will answer the question in terms of that. I think the most difficult thing in the validation aspect, in terms of composite being integrated in battery applications, is that most safety testing is dynamic. And it's more difficult to validate a dynamic test compared to a static test. Also, the behavior of the composite, especially the thermoplastic, which is elastoplastic and very anisotropic in its behavior, it's difficult to capture in homogenized material models used in commercial FE codes. So I think that sums up the difficulty, but it's doable. As you could see, we did it. So it's very interesting.
Thank you very much. Moving on to extended.
Yes, if I want to make an analogy, it's like university or friendship. The first 6 months is very interesting until the exam time. So when it goes to the real life, it's getting complicated. So first point that I have experience on the cell level, so you can test. Then on the module test, you do, and then you do the component again and again and again and again. And then the issue happens when you want to go to the integration part. You have a person speak Japanese, a person speak Greek, and now they should connect together and be able to work together. They have different cultures. They have different jet lags. And now they should be able to work in a real system, which is harsh. And for instance, one of the projects mentioned, you forgot condensation. You forgot that this system doesn't work with these types of transformers. You forgot that this system is driver's behavior is complicated. Okay, so most complicated part is when you take it into the real life like a child. First, it's fine when it goes to the school, it's fine, and after it's 80 years old, so it might goes to jail or it might goes to a successful person. Finally, I think the most complicated part is the integration part, that everything pops up. I mean, the real exam.
Thank you very much. I have a couple of questions in the chat, so we'll answer them. The two first ones are for Kamil. Did you simulate the TP behavior? If yes, what are the expected results for the TP tests? What software did you use? Did you do cell level TR test for model calibration? And the second question is, do you have nail pen result for your SSSB on cell level?
Okay, let's start with the TP question. So we didn't simulate the TP behavior in this project. We did not have the resources nor time for that, but we do it in general. We use SimCenter star CCM, if I remember correctly, and we do calibrate our simulations with the results from the real tests. Maybe not, on cell level, module pack level even. We use this as the feedback to improve the simulations. Yes, that's what we do with our internal Ion Core projects. Do you have nail results? Well, like I mentioned, we didn't do the nailing tests for the NEXTBAT yet, so no results yet. Sorry.
I think people are really expecting those results, so I guess we'll have to talk to you about it a bit later on. Maybe do a specific post about it, just to give some information. We'll have
maybe
to
next
think about
webinar.
That. Maybe next webinar. Who knows? I have another question to Morshed. How accurate and how much can you trust 1D simulation, mainly thermal simulation results, to the actual pack system?
Very hard, short answer. It's like I want to buy a car. But if I want to make it a little specific, first, even before 1D, for instance, for calculation that the system will explode or not, I mean the enclosure, I even use 0D. It depends on the time, that how much time I have and what type of customer is this. So first we do 0D and understand the very worst case. And then we easily consider the safety factor of 2, or it means 50% coefficient. And most of the time, as a rule of thumb, it works. And then if we have time, then we go to the 1D simulation, which is very, very valuable for me, because 1D simulation is a part that always comes with you. Even later, when you do the 3D simulation, you use the result of 1D simulation for your system that you made. For instance, in a project, we thermal interface material we wanted to change. Thermal interface material is a component that you put between two thermal heat components to reduce the amount of thermal resistance, because air is not a good component. Air is not a good thermal conductor. Even in your IC, you have seen on the cell phone, there is some material that is thermal interface material. For instance, on one of our projects, we wanted to change the thermal interface material. And it was in the phase of mass production. And we understood that those materials we have selected doesn't behave very well because of some physical aspect. It gets torn easily when the operator wants to use it. It's never you can see it in the simulation or anywhere. It's really production. And then thanks to the 1D modeling that we had, we just changed the new materials with the previous one, and we saw that it works. And in that case, we had just 1 degree difference, which is not very low, but at least it saved the project. And we showed to the customer that, man, it's just 1 degree, and at least you have the product. Later, whenever the supply chain respect you, we will replace. So these types of 1D, I cannot say the things that you can go with it, but from my point of view, this is not it is the must. It is not 100% reliable, even though 3D simulation is not, even though prototype is not, but this is one thing that you should always have. But if you don't have any way, and it is the only solution and you don't have time, just some safety factor and 1D simulation will work, even 0D. Finally, it's a trade-off. And one more point regarding the previous question regarding the thermal propagation runaway, regarding the SSSB and the other parts, as these types of cells have a very safest behavior because they have less electrolytes in comparison with the previous generations. If somebody can solve the issue of the price, they take the market. But I'm not sure that it will happen in 5-10 years.
To say on the Ds, 3D, why is it important to develop 3D CFD models? Can someone answer this?
I mean, if I may, for example, for me, developing 3D CFD models, it's really important because it allows us to capture the real physical behavior of the system with much greater accuracy. I mean, we work in 0D, 1D, 3D, and we work with 1D models, as you mentioned, Morshed. You can evaluate all the parametrical studies to change some materials in an easier way, system level evaluations, but 3D CFD models, we make it possible to analyze detailed flow patterns, temperature gradients, and local effects that are quite interesting in the design aspects of the cooling strategies, the positioning of the battery cell. So I think these aspects are really important and are essential for understanding the thermal management, safety aspect, and overall performance and optimization of the main battery system.
Very interesting. I don't see more questions in the chat, but if you have any, keep asking them. I'll ask a new one. How do you implement needed modifications on the product after testing results? Because we're at the validation phase right now and testing. How do you implement that after the testing?
Maybe I can talk from the perspective of IonCore. So we have those phases in the development of our products. So it's pretty iterative with A samples, E samples, and basically, like someone mentioned already, it actually should be pretty iterative process that we start the tests on the cell level or on the part level, and we implement the results into the next iteration of the design. And that way we keep actually improving the whole design. So iterative process, I would say.
And from your testing experience, is it possible to reach thermal propagation stop with high energy cells like NMC?
From our experience at IonCore, it is. We have done it, we have reached it with our products, so yeah, it is possible.
Question for everyone. How is thermal management validated in general? I'm guessing testing, but please, as experts, give us your view on this.
If I may, I don't know. Okay, I mean, the thermal management strategy usually, I mean, the validation, if you are speaking about the numerical aspect, first of all, you test the thermal management strategy, you monitorize the temperature of the system, pressure transmitters, temperature in out, you integrate heat with blankets or with battery cells instead, and you evaluate all these aspects in the numerical situation. You evaluate the pressure drop curves of the cooling strategy, and you match the results. This is the results, and after that you match the delta T of the whole channel, the thermal distribution imaging of the cold plate, and all this stuff. This is how we validate the cooling strategy in the numerical aspect, and some other parameters, but I'm not going to start defining all the list. And experimentally, what you have to do is evaluate how much heat you are going to create in the battery system, and considering that, how much you have to integrate a system that can absorb this amount of heat from the battery. You have to develop the strategy, and if you put if you are using a indirect liquid cooling strategy that is based in cold plates, you have to define all the cooling strategy that is from the battery cell to the cooling plate, integrating thermal interface material. You have to evaluate all the resistance network between the cooling strategy and the battery cell, and after that you have to evaluate how you are going to extract all the heat from the battery system, and you start validating the cooling strategy considering your application.
And just one question, Manex, if you don't mind. Generally, what is the error that you receive in your applications for your thermal management, not the hydraulic drop pressure most of the times?
Numerically,
if it is.
Yeah. In this case, I finished my doctoral thesis 2 years ago, and in this way, at that investigation level, the difference was below 1%. So
CFD.
It was, in CFD, in the fluid dynamical aspect. It was a nightmare, I have to say. But usually, in a commercial way, you have to go up to 5% and all this stuff.
Less than 5 is fine.
Yeah, I think so, because this is the scientific environment. I mean, you have to publicate all the results. You have some iteration, and I don't know, the meshing approach that you are going to implement in the numerical design. It's going to be really high quality and really computational, not cost effective. But it's the approach that you have to fulfill in this type of investigation levels. But go on.
And just one more question. When you do it, and then how do you come back from the result that you gain and you modify your ANSYS parameters?
Yeah.
How do you get back? I mean, when you validate, so most of the time it doesn't happen that you have the final results. 5%, it's sometimes 10%. How do you handle that process? I mean, when you see the errors and when you want to modify that error, you will start from the scratch, or what do you do? I mean, the process that you think.
But I didn't catch specifically.
For instance, you reach that, I reached the result and it shows the drop pressure of 0.1 bar.
Yeah, imagine that. Yeah.
And then in reality, it happens that no, it's 0.2 bar.
Yeah.
How do you handle this? You start from again the whole simulation, or?
You start, I understand you. You start by the CAD process. After that, all the iteration. You have to evaluate the error, the level of the error. I mean, if it's a huge error or huge difference, maybe you have to focus again from the beginning, evaluate all these aspects, evaluate if there are some differences, and after that start again with all the process. I know that it's sometimes an iterative process that it's not so cost effective, but sometimes it's better to do it in the preliminary process of the design, all these aspects, instead of considering that at the end of the production aspect you have something that is not working properly.
Just make it clear for everyone that why this CFD is really complicated. Just let you know, some of the random numbers are generated based on turning liquid on some components, and if somebody can simulate it, it can hack all the world. So it's really complicated.
Totally agree.
Very, very interesting last question and discussion to have. But that brings us to the end of today's session. I would like to thank all of our great speakers. Thank you all for the preparation for this webinar, for the time you spent, and for the presentations. I think it really helped everyone. Thanks for sharing your expertise. And again, stay connected with the EU-INGENIoUS Battery Clusters via social media and our different project websites for updates or upcoming events and project progress. All of the project's web pages are accessible, and you can also find them on social media. If you have any questions regarding the presentations or what happened today, feel free to contact me. You can see my email here. And I'll put you in relation with either the different speakers if you have specific questions, or if you want maybe the slides, so you can get in contact with me. The recording from today will be available shortly on YouTube, on the YouTube channels of the different projects, if you want to go back to them and look at specific discussions we had today. I hope it was interesting for you all. Thanks for joining, and have a very good day.
Thank you all.
Thank you.
Have a nice
You too.
day.
Thank you very much.
Thanks a lot. Bye.
Bye.
It was a pleasure.